So let's see if we can pick that back up. So again, measuring L is going to be pretty easy. An understanding that we want a very slow, gradual decline in elevation, okay, to keep the speed of the stream really low. And here you got a very rapid decline of elevation, so you have a very rapid increase in speed, which can be destructive. From here to here, you want a very slow, gradual decrease in elevation. So measuring this length L will be pretty easy, and we want theta to be pretty small because we want this delta Z to be small. And if I need to try to figure out this X value to figure out the Z value, well, the best I can say is L and X are going to be very close because theta is going to be very small, therefore the cosine of theta is going to be very close to 1, therefore X is going to be very close to L. Okay, and that's what I'm saying here. X is approximately L, assuming theta is very small. So if X is approximately L, right, we understand that, and then we say, well, in addition to that, let's move down here a bit. In addition to that, what I'm really after here is the change in elevation. So delta Z, the change in elevation, which is going to equal X tan theta, right, because this tan theta is opposite over adjacent. And again, we're saying that X is approximately L, so L times the tangent of theta. Okay, and that represents delta Z. So what we normally do is we say, well, if we define this S naught, which is equal to the tangent of theta, and it's basically the rise over run, if you will. It's the change in the Z elevation divided by essentially the length. Right? Let's say just length. Okay, we're saying the bottom slope, right, S naught, which we call the bottom slope, that is equal to, again, the change in elevation per unit length of the stream bed. And so what happens then is that the change in Z is approximately equal to this length times the tangent of theta. Well, this is the tangent of theta. This is length times S naught. Length times S naught gives me the change in elevation. Okay, so with this in mind, the bottom slope is length per length. It's the tangent of theta, it's the length per length. It's the change in elevation divided by the total length. Multiply that by the total length, you get the total change in elevation. That's all we're saying. Okay, so with that in mind, let's talk about concept we call uniform flow. So this is a common thing we'll use in open channel flow design, is a concept called uniform flow. According to the slide here, the uniform flow says that if the slope is constant, S naught, and if S naught doesn't change, if the slope is constant, and the head loss due to frictional effects is constant or equal, the depth of flow and the average flow will remain constant. Constant depth, constant speed. So if they tell you, and we'll see this a little more when we talk about the conservation of energy, but if they tell you that you can assume uniform flow, they're telling you you can assume constant depth and constant speed. And this is because, the reasons for this is that S naught is constant, and the Darcy friction factor, or the frictional effects, is constant. And if both of those are true, then these also end up being constant. It's just, again, we can see that when we talk about the conservation of energy. It's a little tough to see right now, But that's what they're telling you. When you know it's uniform flow, we know these two are constant because these two are constant because we know it's uniform flow. Okay. So again, more on that as we progress. Okay, quickly here we can talk about critical and subcritical flow. If I throw a pebble into a stream, okay, you observe so think about taking a rock and throwing it in a lake or a river or a stream in some body of water. You take a rock or a stone or some object, or you just want to unplug, throw your cell phone out there, whatever, throw some object out in the middle of a body of water. Okay? Notice that there's going to be ripples moving away from the point where that object enters the water. Right? Now, what happens to those ripples? Well, if it's a really slow-moving stream, those ripples will move upstream and downstream. Right? Especially if it's like a lake. A lake is a really, really slow-moving body of water. Most lakes are not still. They are actually flowing because they're fed by a river on one end, and often we've made a man-made dam on the other to slow it down. But if I throw a rock into a lake, well, ripples are going to go in both directions. They're going to radiate outward. A very nice, calm, slow-moving creek, if you throw a pebble or a rock into that, you're going to see some of the ripples are going to move upstream. They're going to move against the flow. We call this subcritical flow. The fluid, the average speed of the water is not so fast that it will actually sweep the ripples downstream. So what that means is that we can have events occurring downstream that will actually influence the events upstream. And this is a very important concept. It's not going to be critical for no further than we're going into chapter 13, but it's worth mentioning here. Something kind of interesting to think about. However, if the stream is moving quickly, when you throw something into the stream, again, it's going to cause ripples, but if the stream is moving so fast, it's moving faster than the ripple waves can propagate, the ripples get swept downstream. We call this supercritical flow. That means that the flow is moving at such a rapid pace that events downstream are not going to affect what occurs upstream. And this is supercritical flow. And we measure that with a dimensionless quantity. You see this sometimes. This is a nice chapter 7 Buckingham Pi theorem problem. Sometimes it shows up. The Froude number, a dimensionless quantity, is the speed of the that has to do with the speed of the flow of the stream divided by the square root of gravity and a characteristic length, which normally is just either the hydraulic diameter of the cross section or a lot of times just the depth of flow. Anyway, we can measure the Froude number, and the Froude number tells us whether we have subcritical or supercritical flow. If we have a Froude number greater than 1, that means the flow is supercritical, and that's often we will want to design floodways or spillways where we have supercritical flow. We want, if we have some kind of bottleneck or something changes downstream, we don't want that stacking flow up and causing ill effects upstream. Okay. So anyway, kind of a neat thing to think about. It's not going to really directly impact what we're doing now, so let's keep moving. Something that is going to directly impact what we're going to do, we're going to talk about the Manning equation just a little bit, and the Manning equation deals with either hydraulic radius and or hydraulic diameter, depending on which version we use. Now, we've talked about the hydraulic radius, we've talked about the hydraulic diameter. I don't think we've talked about the hydraulic radius. All right, so the hydraulic radius is going to be the cross-sectional area divided by the wetted perimeter. And the hydraulic diameter, we did see this in chapter 8. We didn't make too big a deal of it because normally we're dealing with circular pipes, but the hydraulic diameter is going to be 4 times the cross-sectional area divided by this wetted perimeter. Now the wetted perimeter is the length, the total length that is in contact with the fluid. Notice this ends up being 4 times the hydraulic radius. Okay? So if I've got a channel here, let's say I've got fluid, let's say I've got a roughly square or rectangular channel, and I've got fluid in here. And let's say I've got length A and length B, right? And this is length B all the way up to the top. Okay? So the hydraulic diameter is going to be 4 times the cross-sectional area. Now that is the area of the fluid, not the, notice if it's all the way full, it's up here at B, but it's not. It's only up here to A. So the cross-sectional area is going to be A times B, divided by the wetted perimeter. Well, that's the length of surface that's in contact with this fluid. So I've got length A here, I've got length B here, and then it comes back up. It doesn't go all the way up to B. It only comes back up right here. This is length A, and it comes up here. So the wetted perimeter, again, the total length in contact with the fluid, that's A, B, and back up to A. I don't worry about this that's open. Right? This is not wetted pipe or wetted conduit. This is not area that's in contact with the fluid. It's only the conduit that's in contact with the fluid. A down, B across, A back up. A plus B plus A. This will give me my hydraulic diameter. And again, hydraulic radius, if I needed it, I just wouldn't have this 4 there. Okay. All right, so that's pretty simple. As the stuff we calculate goes, that's one of the simpler things we can calculate. Okay. All right, so let's talk about the conservation of energy as it applies to these things. Go back. How am I on time? Okay, I can get started here at least. Pull my notes here. All right, so the conservation of energy. Let's say that I've got again, I'm looking at a cross-section. I'm pretending that I can see through the ground or whatever this conduit is contained within. I'm going to make sure I'm on the screen. Yeah. So I want to make sure I can see inside of the conduit or whatever contains this fluid. I've just got fluid flowing down this hill here. So that's kind of what I'm looking at. Okay, so let's say I've got fluid flowing down some kind of a conduit here. And let's pretend that I can magically remove the conduit and just look at the fluid as it flows through the conduit. So that's really all I'm looking at here. So if I look at a point 1 there and a point 2 down here at the outlet, okay? And if I look at the conservation of energy expression here, and I think we can just use let's just do this. Let's say I've got P1 over rho. Let's do it in head form. So it's going to be over rho g plus V1 squared over 2g. Let's not worry about the alpha value, plus Z1. That's going to equal P2 over rho g. There's no pumps or anything like that. It's just fluid flowing from one end to the other. We'll pick up there on the next video.